Hi, and welcome to the AMIA Clinical Informatics Board Review course. I'm Bimal Desai. I'm the lecturer for the Clinical Decision Making course, Lecture 2A1. This is the core content that will be covered in this lecture, specifically bullet points 2.1.1, the nature and cognitive aspects of human decision making, and 2.1.2, decision science. And here's the core content that we'll cover. Here's the learning objectives for this lecture. Make sure, again, that you are studying the 2x2 contingency tables, decision analysis, and some of these other topics that are certain to show up on the test. So the crux of how we make decisions in healthcare is that they involve uncertainty and that they also can involve risk. Until you are certain of a diagnosis, you are in a state where there is lots of uncertainty. And we actually never really know what the true outcome of therapy is going to be until we actually reach the endpoint. So healthcare lends itself really well to decision-making analysis, especially because we can characterize the risk of certain types of interventions. We can characterize patient-specific risks, and many of these things lend themselves to decision tree analysis that we can do. One of the key concepts here is the difference between value and utility. And to explain this difference, I'm going to walk you through an example. Imagine that you are walking down the street and you get invited to participate in a gambling exercise. Someone says, listen, I'll give you $1,000 if you win the game. And here's the rules of the game. You have a 1 in 80 chance of winning. If you win $1,000. If you play this gamble and you lose, you get nothing. And if you simply walk away, if you don't play at all, you're guaranteed $10. So at face value, it sounds like maybe you don't have much to win or maybe you don't have much to lose, but you can actually calculate the expected value of this proposition. And the way you do it is by multiplying the expected outcome times the probability of that outcome happening. And so in this example, we know that there's a 1 in 80 chance of winning $1,000, represented here by the 1,000 times 1 over 80. And there's a 79 out of 80 chance of winning nothing, which is represented by the second half of that equation, 0 times 79 divided by 80, which gives you, if you add that together, a cumulative value of $12.50, which means that on average, if you played this game enough time or if enough people participated in this game, that the average payout would be $12.50. Remember that if you don't play at all, you're guaranteed $10. And this suggests that on average, one should gamble, one should participate in this gamble. Of course, at the individual level, there's no way you could get $12.50. You either get $1,000 or you get nothing or you get $10. But in the aggregate, this model favors gambling, and that's what we mean by the expected value. The expected value of participating in this gamble is $12.50. Now, the expected utility is a little bit different. Utility is a function of value, but it's also a function of the individual's level of risk aversion, their personal preferences, and other monetary circumstances. So, for example, if you desperately need $10, you might choose not to gamble. You will choose to just walk away and pocket the $10. If, however, the $10 is not that enticing to you or you're a risk taker, you might choose to participate because of this slight but discrete risk of winning $1,000. So switching gears a little bit, let's talk about sources of decision bias. The human mind is especially prone to certain types of predictable decision bias. And one way to think about it is what happens when we first encounter a patient. The process of diagnostic inference has been described as this problem of revising opinion with imperfect information. So in bits and pieces, we learn things about patients based on their history, their physical, their appearance, their prior medical records, from lab testing that we do, and so on. And so you can almost imagine it like a funnel. In fact, this author, Blois, described that when you first see a patient, the breadth of your diagnostic considerations are quickly refined and rapidly refined based on the things that you see, observe, palpate, auscultate, measure, and so on. And over the course of your interaction with a patient, you're constantly refining this differential diagnosis in a way that's not too dissimilar from funneling information. The problem is that the way that we funnel that information is very subject to predictable patterns of bias. And these biases take place in the form of shortcuts, mental shortcuts, or what are known as heuristics. And here's an example of some of these common heuristics. Here I'm using the word heuristic to mean a shortcut or a cognitive blind spot or a cognitive bias, you'll hear them referred to as. And one of the most common ones is something called the availability bias. This is the tendency to overestimate the probability of unusual events because of recent or memorable instances. So, for example, if the last patient that you saw with a headache ended up being diagnosed with a brain tumor, it's going to be at the front of your mind the next time that you see a patient with a headache. And unfortunately, this doesn't take into account the pre-test probability of something as rare, hopefully, as a brain tumor. And so this availability bias, this tendency of our brains to remember the most recent or the most memorable case of something often leads us astray. It might lead you to test more than you need to. It might lead you to work up patients unnecessarily. Another decision-making bias that we commit is something called the representativeness bias. And in this case, we overestimate the likelihood of a rare disease by matching patients to the typical picture of that disease. And in the words of this statistician Huninck, the representative heuristic is insensitive to pretest probabilities. So we might think that just because the patient matches a vignette of a specifically rare disease, that the patient must have that disease. And the protection, the adage that we hear against this is this one in medicine. When you hear hoofbeats, you should think horses, not zebras. And that is it's a very specific warning against the representativeness bias. In other words, a even slightly atypical presentation of a common disease is still going to be more common than a very typical presentation of an uncommon disease. Another example of the representativeness bias is the way, unfortunately, that we're actually taught to study for things like the board examination. And all of us can remember from our medical boards the vignette of the rose gardener who has lymphadenitis. And many of you would probably remember that must indicate that the patient has something called Sporothrynx schenkii. I've personally never seen that. I've seen plenty of patients who have lymphadenitis, none of whom have had this disease. And so when you see a patient who has lymphadenitis, the fact that they're a gardener does not necessarily increase your suspicion for something as rare as Sporothrynx schenkii. Here's some other examples of common heuristics. The ascertainment bias. This is where your thinking is shaped based on your prior expectations. And this is a fancy way of saying a stereotype, that you have a specific preconceived notion or preconceived expectation of what a patient should or should not be presenting with. And so these include flat-out stereotypes or things like gender bias. Another one is something called the confirmation bias. This is your tendency to look for confirming evidence but discounting evidence that refutes it. This is another way to phrase this is that you're basically cherry picking. You've concluded in your mind that the patient has a specific disorder, and therefore when you're looking through the medical record for the history, the physical, the lab tests, you're only considering the information that supports your preconceived conclusion and not the alternate diagnoses. Related to that is something called diagnostic momentum. This is the idea that things that are initially considered basically diagnostic considerations, uncertainties, but possibilities, as they are passed from one person to the next, sort of pick up momentum until they become stickier and stickier and perhaps even more certain. So the patient who has suspected appendicitis has probable appendicitis at the next handoff and has likely appendicitis and eventually ends up in the OR simply because of of errors and handoff and this idea of diagnostic momentum. These are the last three heuristics or cognitive biases that we're going to cover. The first one is called the anchoring bias, which is the failure to adjust the probability of a disease or outcome based on new information. And interestingly, this is the one that is associated with conditions like sleep deprivation. So if a resident has been on call for 36 hours, he or she is actually less able to assimilate new information than they were had they not been sleep deprived. And so the error tends to go like this, that you were told in sign out that the patient had a specific condition, that they have a viral infection and not a pneumonia. And therefore, even when the patient started to decompensate and require additional oxygen, you didn't consider that it might be pneumonia because it wasn't in the handoff. You had already anchored on the diagnosis and therefore were unable to assimilate the new information. Related to that is an error called premature closure, which is that you've accepted a diagnosis before it's fully confirmed. And the warning against this is the phrase or the statement, when the diagnosis is made, the thinking stops. The last one we'll cover is called the value-induced bias. And this is one that could work either way. You could either overestimate or underestimate the likelihood of a disease. And it's basically you're influenced by the value that you associate with a specific outcome. This is a really good reason to not treat your friends and loved ones if you're a practicing clinician, because none of us want to imagine that our friends or loved ones would be ill, and so we are subject to all kinds of biases, either overestimating or underestimating the likelihood of disease in those friends and family members. So, for example, you might be so concerned that you don't want to miss a brain tumor in a patient with a new onset headache that you want to get a head CT, even though in your heart of hearts and with your best clinical judgment, you don't really suspect it. It's just that the value you associate with either this person having a brain tumor or the idea of you missing a brain tumor is so compelling that you feel like you must do it. So in the previous few slides, we covered a lot of common biases. There actually are a lot more, and I would refer you to this paper, and the paper is listed at the end by Crosscarry. Crosscarry also listed a number of strategies to defend against cognitive biases. And the most important one here is education. That knowing about cognitive biases in and of itself is an important defense. So, for example, developing insight and awareness into how humans make mistakes when making medical decisions, in sort of forcing yourself to consider alternatives so that you don't have premature closure or anchoring, in something called metacognition. So this is thinking about how you think. So what was it that led you down a specific diagnostic path? And is it possible that you committed an error, one of these cognitive biases, in doing so? There's also a whole list of these that I think are interesting because they are things that we can influence through the design of the electronic health record or through thoughtful use of clinical decision support. So, for example, we use electronic health records very commonly to decrease reliance on memory. And we know that decreasing reliance on memory is a form of defense against cognitive bias. Also, using cognitive forcing strategies, forcing the clinician to go through a specific clinical pathway, forcing them to do a specific test in a specific sequence, rather than jumping to more expensive or less expensive tests, is an important function of clinical decision support. It's also an important defense against cognitive bias. And finally, making specific tasks easier. So if certain decisions require complex information being displayed in a very specific way, or if you can make the decision more easily because a piece of abnormal information is called to your attention, that's certainly within the realm of clinical decision support and something that we can help with to prevent cognitive blind spots. So now let's start talking about some of the mathematical applications of this. And I think this is a fascinating topic to talk about decision analysis. So this is how you can use probabilities to actually decide between different therapeutic options or alternatives. And it's based on this notion that if you consider all the options that are available to you in a given scenario, all the possible outcomes, the sum of the probabilities for those options or outcomes must equal 1. So if you're evaluating a patient and you think that the patient might have a 10% probability of having HIV, that means that they have a 90% probability of not having HIV. And so it's notated this way, where you say P parentheses and then the event in question. That means the probability of HIV plus P parentheses not HIV. And we know that the sum of those two things has to be equal to 1. There's an additional notation that we need to become very familiar with, something called conditional probabilities. And this is, when you speak this aloud, it's the probability of X given Y. And X and Y are separated by a vertical pipe or vertical line. It's a little bit difficult to see in the slide, but in this example, it says the probability of HIV, vertical pipe, IV drug use. And you read that as the probability of HIV given IV drug use, or given the fact that you know the patient uses IV drugs. Another thing we have to be aware of is that sequential events can be described as a chance tree or a graph, and we'll give an example of that, and that you can use this tree to model a decision using the sum of all these conditional probabilities and something called a rollback analysis. By convention, when you draw these trees, the decision node is a square, the chance node is a circle, and the outcome node is a triangle. Additionally, each branch of the chance node, where there is the possibility of a patient taking one out of a number of different branches, is assigned a probability, and the probability of each of those branches must sum to 1. And I'll give you an example of that. Finally, you have at the outcome nodes, these are represented by triangles, and this is where you would assign the expected value or the expected utility of an outcome. So whether it's dollars, and because you're doing a cost effectiveness analysis, or utility because you're trying to assess the patient's preferences, or something like quality adjusted life years, QALY, or some other kind of relative value. By convention, if you're looking at life or death, typically life is represented by a 1 and death is represented by a 0. And then there's this concept of something called a rollback analysis, which is where you multiply the conditional probabilities and you compare the expected value of each branch of the decision node. So let's take a look at a scenario. We're going to look at a hypothetical disease, something called acquired information overloadosis. And this disease is, it's pretty lousy, in fact, that it's fatal 85% of the time if your patient is untreated. But miraculously, 15% of patients have a spontaneous improvement and a cure. Now, let's say that there's an alternative treatment, a new treatment called X. And if you give patients treatment X, their survival does improve from 15% to 20%. So a slight improvement. But there's this, no good deed goes unpunished. There's this unfortunate side effect that 10% of patients who are treated will immediately die on the spot with a fatal reaction. And so the question to us is, which one's better? Should we actually just go with the original standard of care, which leads to an 85% mortality rate? Or can we actually measure whether treatment X is better than the alternative? And the formal way to do that is actually this decision tree. So here I've drawn the tree. You can see that the choice that's represented to us is to either give med X or not. And that's represented by the square node at the far left. The top branch of that represents the yes branch, and the bottom branch represents the no branch. Let's go with the bottom half first. If we don't give medication X, we reach our first chance node, which is represented by the circle. And here there is a chance that's out of our control of the patient either having a spontaneous cure or the disease progressing. And then you can see that the outcome nodes are at the far right, represented by the triangles. Similarly, at the top, if you give the medication, there's another chance node, the first chance node you reach, which is that risk of the 10% fatal reaction listed at the top. And if you go on to survive, not get the fatal reaction, additionally, there's a new chance of treatment success or treatment failure represented by the second sort of nested chance node, the second circle there. Now, this is where we start to plug in the probabilities. And we can see that if you remember from the vignette, there's a 15% chance of spontaneous cure if you don't give medication X. And we know that that means that there's an 85% chance that the disease will progress. And remember that all of the branches at a chance node have to equal 1. And in our example, they do, that 85% plus 15% equals 100%. If we fill in the same probabilities for the top, we know that there's a 10% fatal reaction if you give medication X, and therefore we can deduce that there's a 90% chance that there's no reaction. And if you're in that 90%, you will go on to reach another chance node in which 20% of those patients will have a cure, and that means 80% will have a treatment failure. Now, all of these triangles on the right represent either life or death, and so we can plug in the ones and zeros. If there's a fatal reaction at the top, the patient dies, the value equals 0. If the treatment is successful, the patient lives, the value equals 1, and so on and so forth. So at every outcome where the patient survives, I've listed a value of 1, and at every outcome where the patient does not survive, I've listed a value of 0. And if you look, for example, at the option where you give medication X, there's no reaction, and the patient lives, you can see that there's a 20% chance of 90% that the patient actually will get to that node. So only 90% of patients will have no reaction, and only 20% of those patients will go on to actually survive. So that's the principle behind this rollback analysis. And I'll show you the calculations on the next slide. So here's how we find out the expected value of each of these branches. Remember that the choice represented to us is either yes, we give medication X, or no, we don't give medication X. And I'm going to start with the no branch first because it's simpler. Remember that there's a 15% chance that the patient will survive. And so the value of life or survival in this example is 1. And therefore I can say that 1 times 0.15 equals 0.15. That's in the outcome where there's a cure. In the outcome where there's a disease progression, we know that the value is 0 because we said that the expected value of death is 0. And there's an 85% chance of that happening. And 85% times 0 is still 0. So if you sum both of those expected outcomes, you can get the expected value of that branch, which is 0.15 plus 0 for a total expected value of 0.15. We can do the same thing for the top branch where the patient does get medication X. And the only more complicated thing here is in that branch where there is no reaction. So let's go through them one by one. In the case where there's a fatal reaction immediately after getting medication X, that there's a 10% chance of that happening. So there's a 10% chance of you having an expected value of 0, or 0 times 0.1, which is 0. In the case where there's no reaction, we said there's a 20% chance of living plus an 80% chance of death. And that whole sub-branch of the tree has a 90% chance of taking place in the first place because those are the 90% that survived. And so I multiply all of that by 0.9 and I end up getting 0.18. Now the sum of the fatal reaction and the no reaction is now 0 plus 0.18 or 0.18 total. So what this means is that if you give medication X, the expected value is 0.18, or in other words, 18% of patients would survive overall. And if you don't give medication X, the expected value is 0.15, which means that in our model, giving medication X is slightly better than not giving medication X, despite that 10% chance of fatal reaction. That there's a higher expected value if you give medication X to the patient. So this type of rollback analysis of being able to calculate the cumulative probabilities at a node in a decision tree like that is something that you should be expected to do, you should be able to do. And so what I would do is look at the example, make sure you understand how we calculated these, make sure you understand how we did the rollback analysis specifically for that no reaction branch, where you have to calculate the probabilities at each circle chance node and then apply it to the previous circle chance node in the same tree. So in this example, we talked about it as if we were certain that there was a 10% chance of survival or a 15% chance of death or whatever. The more common scenario, though, is that you know that the probabilities are somewhere in an expected range. And the problem with dealing with those ranges is that if you're on the low end of that range of probabilities or the high end of that range of probabilities, it might make a difference in your decision analysis. In fact, it might change the outcome entirely. And so one common technique to look into that is to do what's called a what if or a sensitivity analysis. And basically what you do is you apply a range of probabilities to your model. And the reason why it's called a sensitivity analysis is because you want to see if the model is sensitive or not to variations in those inputs. So let's change the vignette a little bit and say, what if the probability of treatment success due to medication X is somewhere between 10% and 30%? We're not certain what it is. It's just somewhere between 10 and 30%. Can we identify the threshold at which therapy becomes too risky? Another type of application of this is a cost effectiveness analysis. And I hinted at this before, that we used life and death, expected values of ones and zeros. You can imagine quality adjusted life years. You could just as easily substitute dollars if you wanted to look at the cost of various therapeutic trajectories. And so this decision-making technique, this decision analysis technique using these trees is a way that you can actually do a cost effectiveness analysis as well. So let's look at the sensitivity analysis. Again, notice that what I'm doing is I'm continuously varying the probability of improvement due to medication X. I said that previously I was pretty certain it was somewhere in the middle of that range, but now I'm not so sure, and I think it's somewhere between 10% and 30%, maybe because of new research data that's come out or whatever. The expected value of the standard of care is fixed at 15, and what's represented in this graph here is that at some point there's an intersection between those two lines. That if the expected probability of improvement due to medication X is down closer to 10%, you can see that your standard of care is still better. However, if medication X has an estimated probability of improvement that's closer to 30%, that it in fact is better than the standard of care. And one way to look at it is where those lines intersect. If your true probability of improvement is to the left of that, then you should stick with your standard of care. If your true probability of improvement is to the right of that, you should stick with medication X. And so we would say that this model is sensitive to the range of values for the probability of improvement at medication X. And so we can't conclude with any certainty that medication X is actually better than the standard of care, because it really depends on where it is in that range. So until now, we've talked about the far right side of those decision trees, the value nodes, the triangles, as representing things that are straightforward to measure, like life and death, or monetary value, dollars. But often you want to do something more than that. You actually want to assimilate the patient's own preferences into those values, again, to sort of get at the utility of a health status for a patient. And just to make the point that the therapy that is numerically favorable may not be the one that the patient always prefers, consider these two options for, let's say, treating a malignancy. That in therapy A, there's a 50% chance of 10-year survival, and in therapy B, there's a 90% chance of 2-year survival. If you're going to do this strictly by our previous expected value calculations, you would say that therapy A has an expected value of 5 years. 0.5 times 10 years is 5. And that therapy B has an expected value of only 1.8 years, which is 90% of 2 years. And it should be apparent that it's sort of a toss-up. It really depends on the patient's own preferences. Some patients would take the risk of only a 50% chance of survival if it means the possibility of living for 10 years. Whereas other patients might say, I want the almost certainty of being able to live for 2 years so I can have 2 quality years with my family. And so it's not true that patients would prefer the one that looks like it's numerically favorable, the one that has the expected value of 5 years. So how do we actually assess this? How do we assess the patient's utilities? How do we assess their preferences? Well, there are 3 different ways, or 3 commonly accepted ways to measure a patient's utility for a particular health status. In other words, the degree to which they value a specific health status or status of illness. And these approaches include something called the standard gamble, the time trade-off, and the visual analog method. In the standard gamble, you're asking the patient to choose between X amount of time in a state of illness versus a therapy with a known risk of cure or death. In the time trade-off, you're asking them to choose between X amount of time in a state of illness versus an alternate amount of time in a state of perfect health. And in the visual analog, just like in those pain scales and things like that, you're asking them to rate their health status on a scale where 0 equals death and 100 equals perfect health. So a patient with chronic low back pain might say that their state of health is somewhere around 82. A patient with some other disability might say it's lower or higher than that, and so on and so forth. And so you can sort of start to compare different health statuses or states of well-being based on that. Let's look at the example of how we would measure the quality adjusted life years, or QALYs, using the time trade-off technique. So in this example, I would ask the patient, imagine that you have to live 10 years in your current state of health, whatever that is. Now imagine living for some time period less than 10 years, but in a perfect state of health. How many years of perfect health do you believe are equal to 10 years of your current state of health? So in other words, if I could make your current state of disability or illness vanish, how many years of life would you trade for that? So imagine a patient with debilitating chronic pain, and you say to them, imagine living 10 years with chronic pain. If I could make your pain go away, how many years of perfect health would you trade for that? Would you be willing to live 9 years of perfect health compared to 10 years in your state of pain? And they might say yes. What about 8 years? And they might say yes. What about 7 years? They might say yes. Eventually, you'll get to a point where the patient does not perceive that the loss of years of life, the trade-off, is worth it. So when you get down to, for example, 4 years of perfect health, and they're unwilling to go lower, they would rather live 10 years in chronic pain than only 3 years in perfect health. What you've basically determined is that the patient values their current state of illness, 10 years of living with chronic pain, as equivalent to 4 years of perfect health. In other words, the time trade-off is 0.4. Or, in other words, 1 year of health in their current state of illness is equal to 0.4 years of perfect health. Which means that if you live 3 years with your chronic pain, 3 times 0.4 equals 1.2 quality adjusted life years. So this time trade-off technique allows you to find that point where the patient describes to you that trade-off between health and wellness, health and sickness. And there are sort of established and published quality adjusted life years for various health statuses that have been determined through research. Also, there's one thing to note about quality adjusted life years is that unlike the previous examples of life and death, where 1 was life and 0 was death, you can actually have a negative utility. You can have a negative quality adjusted life year. In other words, there are some states of life that are worse than death itself. And so that's an important distinction for quality adjusted life years. And I gave this example previously of the cost effectiveness analysis you can do with decision trees. You can also do something that allows you to more directly compare the trade-off between money and clinical outcome. In other words, this cost effectiveness ratio, the incremental cost effectiveness ratio, or ICER, that's a technique that allows you to look at this trade-off between the utility of a therapy and its cost. And probably one of the best examples of how this is used in practice is that within the United Kingdom, the National Institute for Health and Clinical Excellence, or NICE, uses quality adjusted life years as part of their cost effectiveness analysis when they choose pharmaceutical options. And in fact, nothing makes its way into the UK national formulary without having undergone this kind of cost effectiveness analysis. You have to demonstrate, for example, that the excess expenditure for some novel therapy is worth or is lower than what's known as the willingness to pay when you do this ICER analysis. So this is the sort of formal description of the incremental cost effectiveness ratio. It's a measure of the change in cost with each change in unit of effectiveness, which is usually or often quality adjusted life years. And because it's a delta in cost divided by a delta in effectiveness, it's basically the slope of a line. You can think of it as what's my change of cost versus the divided by the change in effectiveness. And we'll walk through an example of this. There was a study that came out in 2013 where a group looked at the cost effectiveness of a new internet-based monitoring tool for neonatal post-discharge home care. So in the country where this was conducted, the routine was that all babies who were born in the hospital after discharge had to come back for a neonatal follow-up visit, which cost the health system some amount of money. They were testing whether a web-based follow-up system would be less effective or more effective or cost-effective. And the way they measured it was by looking at this incremental cost-effectiveness ratio. And the outcome of interest was actually, I think it was avoided hospitalizations. And this is what they found. They found that their internet approach, when they looked at the total cost of building and amortized the cost over the number of patients that were seen with this technique, the internet follow-up cost about 86 euros. And compared to the hospital visit, which costs the health system 182 euros. So you can see that the incremental cost of the hospital visit was in excess of 96 euros. But in terms of which one was more effective at preventing readmissions, you can see that the effectiveness of the top strategy was 0.944, and the effectiveness of the hospital visit strategy was 0.842. So the hospital visit cost 96 euros more, but it was 0.102 units of effectiveness less effective, which means that the slope of this line is negative. It has a negative incremental cost effectiveness ratio to the tune of 941 euros. And the way to interpret that, there's two ways to interpret that. The first is that the health system, by using the internet follow-up, would save 941 euros for every avoided hospital visit, or alternately, that it costs the health system 941 euros compared to the internet follow-up if they stuck with the standard of care, which was hospital visits. And you can see in the bullet points at the bottom that a third way, perhaps an easier way to understand what this negative 941 euros represents, is that using the internet strategy, society would save 941 euros for each avoided emergency department visit in the first month of life, which is when this study was conducted. All right, let's talk about a new topic. This is Markov models. So when we did our decision tree analysis, we assumed that there was sort of a linear sequence, that you went from node A to the next chance node to the next chance node, and that you basically only moved one direction through this pathway. And that's not true for many health models. It's not true for lots of decision-making models. And specifically, you can have a situation where there are transitions between states back and forth. And one way to understand what happens with these types of systems over time is something called a Markov chain. In the Markov chain, you have a series of events, each with a known fixed probability of transition within a defined time period. These are, you might hear these referred to as discrete time Markov chains. We make the assumption that the likelihood of something transitioning from one state to the next is stochastic, meaning it's random. And for the purposes of this exercise, we're going to assume that it has no memory. In other words, if you're in one state, the probability that you were transitioning to another state is not dependent on this previous state that you were in. I think there are ways to do it where you can incorporate some memory into the system such that transitioning from one state to the other is influenced from your previous state. But for the simplicity of this model, we're not going to do that. And that's known as a first order or memory-less Markov chain. And what you can see here on the right is a two-state Markov chain. There's two states, one called E and one called A. And all of those arrows have a little number next to them, which shows you the probability of transition from one state to the next within a certain time period. And remember that just like we did with the chance nodes, the probability that you'll transition from one step to another, all of the probabilities around a certain node must equal 1. So look, for example, at the node that's labeled E. You'll see there's two outbound arrows. There's one with a probability of 30% and one with a probability of 70%. And the way that the arrows are written, there's a 30% chance that if you are in the state of E, that you'll remain in the state of E at the next time cycle. And by the same token, there's a 70% chance that you'll transition to the state known as A. Conversely, if you're in A, there's a 60% chance you'll stay there in one time cycle, and there's a 40% chance that you'll transition out in the next in that time cycle. So let's put some actual sort of concrete terms around this. Imagine that this is a Markov model that describes some really simple animal that does exactly two things in its life. It's either eating or it's asleep. And when it's not asleep, it's eating. And when it's not eating, it's asleep. And you want to study these animals, and you imagine that maybe you have 100 of these creatures. All of them at some point in time are in that first state. They're all eating at time 0. So after one time period, how many would you expect to be eating and how many would now be asleep? Well, based on the way the probabilities are set up, it's intuitive that out of those initial 100, we would expect only 30 of them would continue to be eating after one time period, the transition from T0 to T1. And now 70% would be in the next state of A, or asleep. So instead of 100 in E and 0 in A, now you've got 30 critters in E and 70 critters in A. So that was one time step from time 0 to time 1. But what if we want to measure what happens in time 2, time 3, and so on? That's where we have to start doing a little bit more math. Now, this is the formal sort of matrix math way of doing these Markov chains. And I'm going to include this for just general reference. I don't think you're going to be expected to know matrix math for the board examination. There is a less complicated, sort of more informal and intuitive way of understanding these models in the subsequent slides. But I think in order to understand what's going on, you need to understand that the basis of this is this matrix math. So those two states, E and A, and the probabilities of transition from E to A, from E to E, from A to E, and from A to A can be represented as a 2x2 matrix. And this is referred to as a 2x2 Markov or 2x2 stochastic matrix. It's basically a matrix that represents the probabilities of transition from one state to the next in a single time period. So this matrix represents our two-state graph. The way it's constructed, the rows have to add up to 1, and the values must be non-negative. So going from left to right, we are representing this probabilities of transition in the first row for E and in the second row for A. Now the columns represent the next time state at time n plus 1. So I've put in red there, you can see that the 0.3 represents the probability of transitioning from E at time n to E at time n plus 1. That 0.7 represents the probability of transition from E at time n to A at time n plus 1. And you can see that matches what's in the graph. And the second row has that the probability of transition from A at time n is 0.4 as it moves to E. And the probability of transitioning to A, starting in A and ending in A at time n plus 1 is 0.6. Again, consistent with the graph that's there. So far, so good? Okay. Now, that was our probability matrix. We need another matrix that represents the state in which these animals are kind of hanging out initially. And so there's a 1/2 vector. We can't call this one a matrix because it has a dimensionality of 1. But there's a 1/2 vector that represents a starting state where 100% of the animals are eating. So you can think of this as representing the initial kind of starting distribution of these animals. And you can see that the 1 represents that 100% of animals are eating, and the 0 represents that 0 of the animals are asleep. And this is where it gets a little bit tricky. And this is where, if you have learned matrix multiplication or matrix math in the past, it'll be a little bit easier. But if not, again, I'm going to show you the more intuitive way to do this that doesn't require matrix math in the later slides. So if we want to figure out what the probability is at time 1, given that at time 0 they're starting with 100% of animals eating and 0% of the animals asleep, we have to multiply that 2/2 stochastic matrix by the 1/0 probability vector. And the way you do that is you multiply each column in the stochastic matrix by each row value in the probability vector. So follow the colors there. I'm doing 1 times 0.3 plus 0 times 0.4. So I went down on the stochastic matrix and I went across in the probability vector. So that gives me the first value in my new probability vector. And for the second value, I have to do 1 times 0.7 plus 0 times 0.6. And that gives me a new probability vector for time point 1. And you can see that it matches what we kind of intuitively derived in the previous slides, which is that at time 1, you can expect 30% of the animals to be eating and 70% of the animals to be sleeping. And this gives us a way that we can actually continue to do this over and over again. If I wanted to do this at time 2 and time 3, all I have to do is change that probability vector. So instead of 1 and 0, I would now use my second time point of 0.3 and 0.7. So let's do that. Here's my new probability vector. I'm going to multiply it by the same stochastic matrix, and I get 0.3 times 0.3 plus 0.7 times 0.4. That gives me the first value in my new time 2 probability vector. To get the second value, I get 0.7 times 0.3 times 0.7 plus 0.6 times 0.7. Again, each column value in the stochastic matrix gets multiplied by each row value in the probability vector. And so now I know that at time 2, 37% of the animals are eating, 63% of the animals are awake. And I can plug that into the matrix again, and I can get the value at time 3 and so on. And so at time 3, if you go through the math, you'll see that the probability is now 0.36 and 0.64. And you might notice that these values are actually starting to converge. And in this specific example, you actually do sort of reach a steady state of animals between the eating and asleep states. After 3 cycles, at time 3, the probability that an animal is eating is 0.36, and the probability of being awake is 0.64. Sorry, probability of being asleep is 0.64. So you might ask yourself, well, what are the applications of this to healthcare and or informatics? And there is actually a lot. If you want to model a disease progression over time, if you want to do some sort of long-term cost-effectiveness analysis, this actually is a technique that comes in very handy. So here's an example of modeling disease progression. Imagine that we have this three-state diagram where there are three states of health. There's either wellness, disability, or death. You can move, if you start out in the wellness state, you can stay there, you can become disabled, or you can move to the state of death immediately. If you are starting out in the disabled state, you can either stay there or move to death, but you cannot move backwards. You can't move backwards to well in the way that you can see the arrow only points in one direction. And then finally, if you're in the third state of death, you have to stay there. You can't go back to wellness and you can't go back to disability. And these sort of unidirectional arrows are represented in our stochastic matrix. So if I'm moving from the state of wellness to the state of wellness, in this example, there's a 60% chance. There's a 20% chance that you move from well to disabled. There's a 20% chance of moving from well to death. And notice that we said that you can't move from disability back to wellness, and that's represented in the second row of our stochastic matrix, where the probability of moving from disabled to well is 0, and the probability of moving from disabled to staying disabled is 0.6, and so on. And finally, there's no outbound probabilities for death. There's only the single probability that you will stay dead, or 100%, or that's why there's a 1 in the bottom right value there. And there are terms for these kinds of states because you can only move in one direction through the state of disability. It's known as what's called a tunnel state. You can only move through it in one direction. And death is what's known as an absorbing state because you cannot move out of it. That all things eventually become absorbed into that state. And because we have these probabilities, and let's say, for example, we also know the utility of each state. We know the utility of being well, the utility of being disabled, and so on from maybe quality adjusted life years. We can model the lifetime utility or the cumulative utility of a hypothetical population as they move through this disease state with their varying probabilities. So, for example, let's imagine you had 10,000 patients who started out well, and you put them through this Markov chain. What you would expect after one cycle is that 6,000 are now continue to be well, 2,000 are disabled, 2,000 are now dead. For a cumulative utility, and this I don't have the actual values that they use to calculate the utility here, but in this example, the cumulative utility was 7,400. And then you do the chain again, multiply that matrix by the vector, and you get 3,600, 2,400, and 4,000, and so on and so on and so on, until, in this example, it takes 24 cycles to pass all of those 10,000 initial patients to the final state of death. And again, at each cycle, I can measure the utility, the sort of instantaneous utility at that one cycle. And if I sum it all up, I can see that those 10,000 patients who started out in the state of wellness in the top left accrued a total utility of 23,752, and which means that on average, they each had 2.3 units of utility, whatever it was in this example, quality adjusted life years. And so that's why these Markov models and Markov chains can be useful. Another interesting example, one that's more relevant to informatics, was this novel paper by Kai Zhang and colleagues in 2009 in JAMIA, where they looked at the probability of transitioning from one view of the electronic health record to another. In other words, they observed providers using this system, and they watched as they moved from one state to another. And in the publication is this fascinating diagram that shows what looks an awful lot like a Markov chain that indicates the likelihood that if you're in one specific view of the electronic health record that you'll transition to another one. So, for example, there's a 15% chance that if you're looking at the history of present illness, which is that first large circle on the left, there's a 15.4% chance that you will transition all the way to the orders activity. Or if you're in the medication section labeled by the node with the big letter M, there's a 24.5% chance that you're going to go directly to the orders activity. And what they found was that there are these sort of high probability pathways moving from physical examination to assessment and plan, moving from assessment and plan back and forth to diagnosis and so on, that suggested common patterns of utilization. And what I thought was fascinating was that you could actually use this to come up with sort of an ideal interface, that mimics sort of the most probable transition states in how people use the electronic health record. Okay, so as promised, we should do an example of one of these Markov models in a fashion that does not require the matrix math. And let's look at this example here, where there's three states. There's wellness. Let's say this is a population of patients who were diagnosed with a cancer and they were induced into remission. So now we believe that they're well. And there's a discrete probability that they will relapse. And then if they do relapse, there's another probability that they will move on to death. So in this example, there's three nodes: wellness, cancer, which represents relapse, and death. Each with their respective utilities. So the utility of being well is 1, the utility of having relapse is 0.85, and the utility of death is 0. And there are these stochastic probabilities of transitioning. So if you're well, if you're in remission, there's an 80% chance you'll stay there. There's a 20% chance of relapse. Once you relapse, there's an 80% chance you will stay in that state. There's no chance you'll go back to remission again, and there's a 20% chance that you'll pass to the third state of death. And once you arrive in that third state, the absorbing node, you won't go anywhere else. There's a 100% chance of re-entry back into that state. Okay, and let's say that you were posed with the following question. In a cohort of patients, 90% of whom are in remission at the outset of the simulation, and 10% who have residual cancer or relapse. After 2 years, what percent of patients are expected to have relapse? So you're looking at a population where 90% are already in the well state, 10% are in that second state of relapse. And the question is, how many will be in that second state after 2 years? Okay. So here is the non-matrix math kind of intuitive or informal way of doing this. And this is probably the way that you'd want to do it for the board examination. What I've done is I've listed time 0, time 1, and time 2. And for each one of those, I've listed the three states: wellness, cancer, and death. And for each one of those, I'm going to calculate the probability. The problem tells us that the initial probability of wellness is 0.9, the initial probability of relapse is 0.1, and the probability of death is 0. So that's our starting population. And we know from the Markov chain, from the graph on the right, what the probability is that they're either going to stay there or transition to another state. So we can calculate at time 1 that 80% of those initial 0.9, of 80% of the original 90% of patients were going to stay well. And that's represented by the arrow that starts in the well circle and re-enters into the well circle. Which means that after one cycle of time has passed, whereas we started with 90% of patients being well, now there's only 72% of patients are well. Okay? So that's one row of calculations done. Now we're going to go to the next row. In this example, the only way at time 1 that you can be in that state is if you're part of the 20% that entered there or part of the 80% that stayed there. Remember that, see, there's two arrows going into that second node. And we know that the 20% of the original 0.9 or 90% of patients will enter into the relapse state. And we know that 80% of the original 10% of patients will stay in the remission state. So that's where I get the 0.9 times 0.2 plus 0.1 times 0.8. And so after one time cycle, now 26% of patients will be in the relapsed state. Additionally, we know now after one time cycle that some of those patients, unfortunately, who were in the relapse state will move on to the third terminal state of death. And in fact, we know that 20% of those original 10% of patients, or 0.1 times 0.2, will do that. Because there's nobody in the third state of death at the start of this problem at time 0, we have 0 times a probability of 1. And when we add those together, we get that after one time cycle, now 2% of patients in our simulation have died. And so, again, look at the probability vector. Originally, we had 0.9, 0.1, and 0. Now we have 0.72, 0.26, and 0.02. So after one time cycle, the probabilities have changed significantly. But the question asked is what happened after two time cycles. So we have to plug in the new probabilities of 72%, 26%, and 2% back through the exact same calculations. So starting with the wellness bucket, 80% of the new 72% of patients will remain well, which gives us a probability of 57.6 or 0.576. Similarly, if we look at the second state of relapse, there's a 20% chance that if you were well, you've now developed relapse. So that's where I get 0.2 times 0.72. There's an 80% chance that if you started out in relapse that you'll stay there. And that's where I get 0.26 times 0.8 for a cumulative probability there of 0.352. Now, we could stop there because we've already answered the original question. But just for completeness, I've filled out the third row also that shows the proportion of patients that will end up in the third state. And if you go through all that math, what you find is at the end of the simulation, 57.6% of patients will remain well. 35.2% of patients will be in the relapsed state, and 7.2% of patients will have moved on to die from this disease. And so the answer to the question is that after 2 years, 35% of the original cohort is now expected to have cancer. Well, I hope those matrix math examples and Markov chains were as fun for you as they were for me. You probably will see a couple of these Markov questions on the exam, and what I can say is that it's going to be something you'll be able to do using that intuitive second approach. You may not have to use, hopefully you won't have to use the actual matrix approach. If you're more facile with the matrix approach, by all means go ahead and use it. And I think what I would do is pay attention to sort of how we derive those answers. Walk yourself through those examples a couple of times. Make sure you understand the math. Now, switching gears, let's talk about something called Monte Carlo simulation, which is a completely different way of doing these decision analyses. At its core, this relies on the fact that mathematical models can either be deterministic or stochastic. Deterministic models are ones where the variable states are determined by parameters that are set in the model, and so under a certain set of conditions, the model will always perform the same. In other words, you predetermine what the inputs are, and therefore you are guaranteed to get the same output. So, for example, our decision analysis, the trees that we did earlier, those are deterministic because I'm setting what the initial probabilities are, and therefore it's easy for me or straightforward for me to model what the outcomes are. In fact, I'll always get the same outcome as long as those probabilities don't change. In contrast, in a stochastic model, the variable states themselves are determined by probability distributions. And so each time I run the model, I might get a slightly different output. And a Monte Carlo simulation is one of these stochastic models where it says the inputs themselves are variable and have their own probability distributions. And therefore, you have to run the model over and over and over and over again to get sort of an average model or an average output. This isn't totally intuitive, I think, this idea of deterministic versus probabilistic, but I'll try to give you one more straightforward example. All of us are familiar with sort of measuring the area of a polygon, for example, like an irregular polygon. And imagine that you're looking at some crazy object with an irregular shape, and it's irregular enough that you can't measure it directly. In other words, you can't measure the area of this directly. But let's say you put that shape inside a larger shape, like a perfect square that has bigger dimensions than the original odd shape. And let's say that I do know the dimensions of that larger square. If I throw 1,000 darts at that larger square, I can be pretty certain that just by random chance, the probability of one of those darts hitting the irregular object is proportional to the area of that object compared to the largest square. In other words, even though I can't directly measure the irregular object, I can approximate it through simulation by throwing these darts over and over and over and over again. And in fact, the more darts I throw, the more precise my estimate is. And so that's an example of a Monte Carlo simulation where you're using a stochastic or variable method to determine the outcome or to measure something indirectly. And probably one of the best examples of these Monte Carlo simulations, the most recently well-known example, was our own presidential elections and the forecasts that were done by 538, which is the famous political blog. And what this group did, and there's actually an extensive sort of essay on how they did this forecasting, was that they ran 20,000 simulations of the election to estimate the cumulative probability. And they did this with all kinds of variables, such as voter turnout and the post-convention bumps that each candidate would see or not see. And we could argue the merits of whether the final estimates were accurate or not, but this was a very rigorously done example of a Monte Carlo simulation. They were even able to model how that forecast had changed over time due to external secular events like the conventions, for example. So what varied between each of these runs? Well, Nate Silver, the author of the 538 blog, looked at all the polling results and adjusted them based on these secular trends, such as the proportion of likely voters, the popularity balance that a candidate would see after a convention, the adjustments that you'd have to take into account if there was a third-party candidate running, and so on. They also had to, in their model, put in some variation for other kinds of error, such as we know that polls are off systematically throughout the country, so there was a national error factor that was put in there. There's demographic or regional error because some regions tend to poll in one direction versus another. There's state-specific error, and for each of these different variables, they ended up in the cumulative model running this 20,000 times. And again, if you want to know more information about how this Monte Carlo simulation was run, you can refer to the blog post listed below. So what are the applications to healthcare? Well, this is also useful for disease simulation, kind of like the Markov model, but it's especially useful in smaller populations where individual patients probably don't trend to the average. And that's in situations where those Markov models may not work out as well. If you use Monte Carlo simulations, you use the variables to simulate an individual patient's pattern of disease progression and their responsiveness to treatment. And you end up with an output that's a probability distribution for things like the patient's functional status, quality-adjusted life years, cost, and so on. If you want to learn more about Monte Carlo simulation in healthcare models, you can refer to this article by Richter and Mauskopf from 1998. But the thing to remember about Monte Carlo, the Monte Carlo models, is that they involve repeated simulation using these stochastic inputs. All right. So the next half of this lecture is all about 2x2 tables and diagnostic tests and the interpretation of those test results. So this is a good time to pause if you need to, and if not, we're going to keep going. Leonard Mlodinow is the author of this book, The Drunkard's Walk, How Randomness Rules Our Lives. And he was moved to write this book based on a personal story where Leonard was applying for life insurance. And in doing so, he had to undergo a series of health assessments and lab tests. In the process of receiving his lab results, he got a call from his doctor saying, "Leonard, I hope you're sitting down. I have some unfortunate news for you. It turns out that your HIV test was positive, and I hate to tell you this, but you, based on this testing, have HIV." Leonard was aghast. He had no idea that this was a possibility for him. He knew that he was in a low-risk population, monogamous, not a drug user, and really had no explanation for how this could be positive. He was not, a transfusion recipient and so on. And so he asked his internist, "What's the likelihood that this test is inaccurate? Could this be a false positive?" And his internist looked at some of the packaging for inserts for the test, or looked it up online or something, and told him that there was a 99.9% chance that the test was accurate, that Leonard actually had HIV, based on the statistic that he read that in patients with no disease, the chance of a positive test was only 1 in 1,000. Now, let that sink in for a little bit. And what I would suggest to you is that in that statement, there is a huge, huge error, a misinterpretation of these 2x2 contingency tables. And we're going to, hopefully by the end of the second half of the lecture, understand exactly how his internist made this mistake and understand how to not make the mistake ourselves. So let's go all the way back to the very beginning when we're talking about 2x2 contingency tables and ask the basic question, what do we care about with regards to diagnostic testing? Well, there's really only two things that we care about. We care about how we're supposed to choose the test, and we care about how we're supposed to interpret the diagnostic test itself. And in the first bucket, when I'm choosing a diagnostic test, I really want to know, is this test any good? In other words, what is the likelihood of the positive test if the disease is present? What is the likelihood of a negative test if the disease is absent? How good is it? How good is this test at discriminating disease? When I'm interpreting a diagnostic test, I have a related but slightly different set of questions. Specifically, now I want to know, what's the likelihood of disease if the test is positive, and what's the likelihood of no disease if the test is negative? And notice how those four statements, the four questions there, are related. They're actually sort of worded opposite from one another. In the first two, you assume that you know the disease state. You're saying if the disease is present or absent, what's the likelihood of the test being positive or negative? And in the second two, in the case where you're trying to interpret the test, you assume you know the test result, that if the test is positive or if the test is negative, what's the likelihood of disease or no disease? And that's the key difference between when you're choosing a diagnostic test versus when you're interpreting a diagnostic test. And the good news is that a 2x2 contingency table allows us to answer these questions. The way it's set up is, by convention, you list your disease state across the top and your test result across the left. In the top left corner of the 2x2 table is the state where both the disease is present and the test is positive. And if you go through and label them A, B, C, and D, the way I've done here, you can see that they, going sort of left to right and top to bottom, that top left is A, which is your true positives, followed by B, which is your false positives, where your disease is negative but your test is positive, followed by C, which is false negatives, where your disease is positive but your test is now negative, and followed by D, your true negatives, where both the test and the disease are negative. Also notice that the rows, when you add them up, mean something, and the columns, when you add them up, mean something. That the first row, A plus B, is everyone who tested positive, and the second row, C plus D, is everyone who tested negative. Furthermore, each column, again, means something, that A plus C is everyone who in this cohort who has the disease, and B plus D is everyone who does not have the disease. And if you take A plus B plus C plus D, that's everyone in the population. There's a whole lot of other relationships we're going to explore here with these, but those are sort of the basic ones. Now, let's go back to that probability notation that we were talking about. Remember, we say that P parentheses something is read as the probability of that thing. So P parentheses X is the probability of X happening. And remember that conditional probabilities are separated by this vertical pipe. So when you see the notation P parentheses X vertical line Y, that means the probability of X given that you know Y. And this is a conditional probability. So if we look at the 2x2 table, we can say that the probability of disease is A plus C, because that's everybody with the disease, divided by A plus B plus C plus D, everybody in the entire population. In other words, that's the proportion of patients in the population who have the disease. So now let's go through some additional examples. What is the probability of no disease? Well, it should be intuitive that that's B plus D divided by A plus B plus C plus D, because B plus D represents everyone who does not have disease. And what's the probability of a positive test? Well, that's A plus B, everyone who tested positive, divided by the entire population. What's the probability of a negative test? Well, that's C plus D divided by the entire population, A, B, C, D. Okay? Now, let's introduce some new terms. These four terms, true positive rate, false negative rate, true negative rate, and false positive rate, are very important. So I'm going to define the true positive rate as the probability of a positive test if you are known to have the disease. So the conditional probability of the test being positive given positive disease. Okay? And the way that's worded, we know that the true positive rate, or TPR, is equal to A divided by A plus C. So it's among the people who have the disease, who is A plus C, the proportion that test positive, which is A. Similarly, we can say that the false negative rate is going to be C, your false negatives, over A plus C, patients with the disease. And you should note that the false negative rate we've written as C over A plus C, but it's also the same as 1 minus your true positive rate, because we know that A plus C together have to equal everyone in the population. So that's an interesting relationship, that 1 minus your true positive rate is equal to your false negative rate. Keep that in mind. All right, next is your true negative rate, which is D, or your true negatives, divided by B plus D. And next is your false positive rate, which is B over B plus D. And again, this one has a relationship to the true negative rate, that 1 minus your true negative rate is equal to your false positive rate. Okay? So, lo and behold, your true positive rate, your TPR, is a synonym for sensitivity. The formal definition of sensitivity is that it's the probability of a positive test given the presence of disease. And so sensitivity, or your true positive rate, is A over A plus C. And what that also means is that 1 minus my sensitivity is equal to my false negative rate. I think this is probably the most intuitive way to think about sensitivity. When I say a test is very sensitive, let's say that the test is 99% sensitive, what I'm really saying is that it has a 1% false negative rate. So in other words, very sensitive tests, yes, they have a true positive rate, but more importantly, they have a very low false negative rate, which means that sensitive tests are good for ruling out the disease. If I test somebody and they test negative, I can trust that negative result. I can believe that I have screened them accurately and the patient does not have the disease. So a very sensitive test is good for ruling out disease, which makes them very good for screening tests. One way to remember that is this mnemonic device where sensitivity equals rule out or snout. You take the S and the N from the word sensitivity and the word out from rule out, and you get snout. I didn't make that up. All right. Conversely, there's specificity, which is your true negative rate. And again, specificity is, the formal definition is that it's the probability that you will test negative if the disease is absent. Given the patient has no disease, what is the likelihood that the test will be negative? Okay? And 1 minus your specificity is your false positive rate. This has the same sort of relationship as sensitivity did, where when I say a test is very, very specific, yes, it's true that it has a high true negative rate, but more importantly, it has a very low false positive rate. A test that's 99% specific only has a 1% false positive rate. And that means that specific tests are good for ruling in the disease. You can trust a positive result. And that makes specific tests very good for confirmation. The mnemonic for that is that specificity equals rule in, or SPIN, S-P-I-N. So now we've seen how sensitivity benefits, highly sensitive tests benefit from having a low false negative rate, and highly specific tests benefit from having a low false positive rate, which makes sensitive tests good for screening and specific tests good for confirmation. So here's the important things you have to remember about sensitivity and specificity. Both can be phrased as conditional probabilities. Both assume you know the disease state, not the test result. And because of this, they're measures of the test's performance, not measures of the test's utility. In other words, they're useful when you're trying to select the test. They're less useful when you're trying to interpret the result. Also notice that because I can do all the calculations for sensitivity in the first column, and I can do all the calculations for specificity in the second column, that both of these calculations are actually independent of the prevalence of the disease. In other words, the ratio between those who have the disease and who don't have the disease doesn't matter, and that means that these are unique to the test themselves and not to the population that you're testing. Finally, it should be intuitive that there's a trade-off between sensitivity and specificity. That I can make a test almost 100% sensitive just by saying that everyone that gets screened is positive. But the problem with that strategy is that I have an extraordinary number of false positives. In other words, I've traded off specificity. And there is this tenuous balance between sensitivity and specificity, that the more specific I make a test, the less sensitive it is. The more sensitive I make the test, by changing the criterion or the threshold, the less specific it is. And we'll explore that in more depth later. Okay, so we talked about the situation in which we knew the disease state, but not the test result. We were trying to choose which test to do. But what if we know the test result? So now I've tested the patient, I'm staring at this result, and now I need to interpret whether I can trust that result or not, and whether the patient actually has the disease. So in this situation, sensitivity and specificity are not the correct measures. I need two different conditional probabilities. I need specifically the positive predictive value and the negative predictive value. And that's because I'm interested in a different set of conditional probabilities. What I want to know now is what's the likelihood of disease given a positive test, or what's the likelihood of no disease given a negative test. And as I've hinted, fortunately, these are easy to derive and they have their own names. So, positive predictive value is the probability of disease given a positive test. It's A over A plus B. And notice that now I'm looking I'm doing a calculation that does rely on the proportion of those who have the disease compared to those who do not, or the total population. In other words, your positive predictive value does change depending on the prevalence of the disease in the population, because B could be a very, very large number compared to A if A is a rare disease, and that's going to change my positive predictive value. Negative predictive value is the probability of no disease given a negative test. It's D over C plus D. And notice that the negative predictive value also depends on the likelihood of disease in the population, because I'm crossing columns to do this calculation. All right, so here's our summary. These are measures of test performance. Sensitivity, which is equal to the true positive rate, which is equal to recall. And this is a new term for us, but recall is basically in information retrieval, it's synonymous with sensitivity. It gives you the likelihood of a positive test given the presence of disease. Sensitive tests are good for screening for disease, and sensitive tests have a low false negative rate. And again, every statement on this slide, you should be able to, if you can't commit it to memory, you should be able to derive it quickly by just writing down the 2x2 table and proving to yourself how those formulas were originally created. Specificity is your true negative rate. It's the likelihood of negative test given no disease. It's good for confirming a disease, and it has a low false positive rate. 1 minus specificity equals your false positives. And I should have said this earlier, but 1 minus sensitivity equals your false negative rate. On the right-hand side of this, we have the measures of the clinical utility of a test, or the measures of how you interpret the test itself. And these include the positive predictive value. In information retrieval, this is known as precision. It's the likelihood of disease given a positive test. And then we've got negative predictive value, which is the likelihood of no disease given a negative test. Another note on recall and precision. You may be thinking, well, what does information retrieval have to do with diagnostic testing? The relevance is that basically, let's say you have a search strategy and you're trying to look at a corpus of text. The recall of a search strategy is defined that given a search term in the corpus is relevant, or that a document in the corpus is relevant, what's the likelihood that you will find it with your search strategy? That's recall. And precision is, again, analogous to positive predictive value. Given that your search strategy found a document in the corpus, what's the likelihood that it was relevant? So it's very similar to diagnostic testing. All right, let's do a quick exercise. I've got 4 clinical scenarios here and 4 terms on the right. And we're going to match each clinical scenario with the relevant or best statistic that you're trying to optimize. So if I'm testing for tuberculosis in a patient with a positive PPD, which of these 4 statistics do I care about? So remember, a PPD is a screening test for tuberculosis. And once you have a positive PPD, you have to go on to do a confirmatory test. So in this case, I need to pick a test that has a very high specificity. In the second example, screening for Ebola among travelers returning from West Africa. Well, some of this, the hint is in the name, is in the example itself, but I'm looking for a very, very low prevalence disease, and I want to screen for it. And by the way, I can't afford to be wrong. So I need a test that's very sensitive, because I can't afford a false negative. I can't send a patient home who has Ebola and I didn't detect it. In the third example, I have a patient with a negative urinalysis, and I'm using that urinalysis as the basis for deciding to omit a urine culture. So this is a febrile infant. I'm saying, you know what? I trust my negative urinalysis. I don't think this patient has a urinary tract infection. I'm not going to do the urine culture. Which of these 4 statistics do I need to optimize to be able to make that decision safely? And the answer there is the negative predictive value. I need to be able to reassure myself that If the test is negative, that means the patient does not have the disease, and therefore it's safe to omit the urine culture. And finally, how do I interpret a positive rheumatoid factor in a patient with no signs or symptoms of autoimmunity? I've done this test. Now I've found that it's positive. I need to figure out what that represents. What I care about here is the positive predictive value, the likelihood of disease given a positive test. One more time, and hopefully you're getting the idea that this is an important topic for the examination. Each of these four things can be expressed as a conditional probability. In sensitivity and specificity, it assumes you know the disease state. Positive and negative predictive value, it assumes you know the test result. So sensitivity is, given the presence of disease, what's the probability of a positive test? Specificity is, given the absence of disease, what's the probability of a negative test? Positive predictive value is, given a positive test, what's the probability of disease? And negative predictive value is, given a negative test, what is the probability of no disease? Also, you have to remember that two of these things, sensitivity and positive predictive value, have analogous terms in information retrieval. That recall is the same thing as sensitivity, and precision is the same thing as positive predictive value. This is those same four conditional probabilities written in our vertical pipe notation. I would just commit these to memory. And here's a class exercise. Let's do this one together. In 1998, there was a study that looked at the performance of various urinary tract infection screening strategies in infants. And what they were looking at was the utility of a test, this urine dipstick, and where they defined a positive dipstick test as being anything greater than trace leukocyte esterase or presence of nitrites. And what they found was that using this definition of a positive dipstick test, out of the 3,394 patients total who they tested, all of whom underwent urine culture, 95 of those 3,394 tested positive. And what they determined was that this dipstick test in that population had a sensitivity of 79% and a specificity of 97%. So there's two questions here. One of them is, what was the baseline prevalence of disease in this population? And the second one was, what is the rate of urinary tract infection in those patients who had a positive dipstick test? And you may be thinking, well, I'm not sure how to answer either of these. They don't reference or they don't ask specifically for sensitivity or specificity or whatever. And that's a true statement. But you should also be able to figure out that one of these two things actually refers to a conditional probability that we've seen before. So let's look at this example in more detail. The first thing I would do if I were taking the boards and I was confronted with that question is I would draw my 2x2 table and I would start to fill in the numbers that I know. So again, disease state on the top, test results on the left, yes is in the same corner, or positive is in the same corner. I know there's 3,394 in the entire population. I know that 95% of them were documented to have a urinary tract infection according to culture by the gold standard of a urine culture. Okay? Now, I also know, because I know the sensitivity, I know the proportion of these patients who had a positive dipstick test, right? The definition of sensitivity is, given the presence of disease, what's the likelihood of a positive test? And because we know that, I can multiply 95 by the sensitivity of this test, and I can get 75. So if 75 patients had a positive dipstick test and there were 95 patients total, I can do some simple math and figure out that 20 of them tested negative, even though they had a urinary tract infection. In other words, I had 20 false negatives. Because the rows need to add up to the sums on the right, and because I know there's 3,394 patients in the entire study, of whom 94 had a urinary tract infection, I can calculate that 3,299 of them did not have a urinary tract infection. And because I know the specificity, I can figure out how many patients were true negatives. So if I take the specificity, multiply it by 3,299, I find out that there's 3,200 patients who had no urinary tract infection and who did not have a positive dipstick test. And that means that 99 of them had a positive dipstick test but did not have a urinary tract infection. In other words, there are 99 false positives in this cohort. And then I can sum across to get 174. And I need that number for the second part of this question. Finally, I can figure out 3394 minus 174 is 3220. And I've completed my 2x2 table and all the column and row values, and I have enough information to answer my question. So the first question was, what was the baseline prevalence? And we know from our previous slide that 95 out of 3394 patients had a positive urine culture. That means that the baseline prevalence was 2.7%. The second question was, what's the rate of urinary tract infection among those patients with a positive dipstick test? And this is where I need that first row of information. Notice what they're asking here. They're saying, what's the probability of urinary tract infection given a positive test? And that should really remind you of one of the conditional probabilities, specifically the positive predictive value. What's the likelihood of disease given the positive test? So what they're asking when they say what's the rate of UTI among those patients with a positive dipstick is, what's the positive predictive value of this test? And in this example, it was 75 out of 174, or 43%. And you might be thinking, well, that's lousy. That's less than a coin toss. That's worse than a coin toss. I'm not that certain that this patient has a urinary tract infection. But look at how your pre and your post-test probabilities have changed. In other words, when this patient walked in the door, when one of these patients walks in the door, I'm only 2.7% certain that they have a urinary tract infection. Of all comers in that cohort, there's a 2.7% chance of a urinary tract infection. And simply by doing this urinalysis, this simple test, if they screen positive, I now am 43% certain the patient has a urinary tract infection. And that's probably enough to actually do additional testing, like a culture or something like that, or empirically treat. So the baseline prevalence of the disease, in this example, you can think of as the pre-test or the prior probability, right? The likelihood of disease before we did the test. And the post-test or posterior probability is basically our positive predictive value, that now they're 43% certain that the patient has a disease. So back to poor Leonard, the author whose internist told him that there was a 99.9% probability that he had HIV, based on this thing that his doctor had read that said that in patients with no disease, the chance of a positive test was only 1 in 1,000. Or rather, he was saying the chance of a negative test was 999 in 1,000. So his doctor looked up the specificity. He said that given no disease, the chances of a negative test is 999 out of 1,000. And from that, he calculated the false positive rate, which is 1 in 1,000. But we know from doing this exercise with these 2x2 tables that that's not the same thing as the positive predictive value. So Leonard asked, given that I tested positive, what's the likelihood that I have the disease? And what his doctor quoted to him was the false positive rate, which is very different. All right, so now we talked about how sensitivity and specificity are not dependent on the prevalence of a population, but how positive and negative predictive value absolutely are dependent on the prevalence of the population, of the disease in the population, based on the simple fact that they require data from both the column of patients who have the disease and the column of patients who don't have the disease. To make this point more clearly, let's look at a commercial HIV test This is one that has a published sensitivity of 99.9% and a specificity of 99.8%. These are exceptionally good tests. And by the way, when I'm saying that a test has a specificity of 99.8%, what I'm really saying is that there's a false positive rate of only 2 out of 1,000, right? I'm saying the false positive rate is 1 minus 0.998, which means that I should not see a whole lot of false positives, period. So how does the disease prevalence actually influence the positive and negative predictive value? So here's a table. I got this from the CDC website, and it shows how you can model the performance of this HIV test, this extraordinarily good HIV test, in populations that range in prevalence of HIV from 10% all the way down to 0.1%. And you can follow along with this by doing the 2x2 tables on your own, but you should convince yourself that, notice that the false positive number doesn't change. The specificity in a hypothetical population of 1,000 patients means that you'll always see roughly 2 false positives because the specificity is 0.998. But also notice that the prevalence changes the true positive numbers, that if it's 10% prevalent, there's 100 people who actually have the disease. If it's 5% prevalent, there's 50 people, and so on and so forth, all the way down to only 1 in 1,000 patients who actually have the disease. And because that number changes so dramatically, even though the false positive number stays pretty fixed, your positive predictive value changes. So in the high prevalence situation where where 10% of the patients are expected to have HIV, the test has a positive predictive value of 98%. It works really well in that high prevalence population. But in a very low risk population, something weird happens. The false positives outnumber the true positives. And so in the population where the HIV prevalence is 0.1%, your positive predictive value is only 33%. And that means that there's a 2 in 3 chance that a test is false. And that's the exact situation that Leonard found himself in. Now, there's an important thing to understand here, which is that this is just basic biostats, that no matter how good your test is, in this case, we're looking at a test that's 99.9% sensitive, 99.8% specific, you can't get over the fact that rare diseases are rare and that at some point your false positives are going to outnumber your true positives. So now let's do another example. Let's say that I'm trying to create an email filter in my email client. And I'm going to create this filter by looking at specific phrases, things like the words opt out, or do you want to unsubscribe, or do you want to change your mailing preferences, all the kind of required verbiage that a lot of spam or vendor or other types of emails will have at the bottom of their generic mailings. I don't know if your email is like mine, but I get like 100 of these per day, and I've had to create this crazy filter specifically to try to keep my inbox a little bit clean. So I've crafted my filter such that it looks for these keywords, and after a day of running the filter, what I find is that 34 emails were trapped by the spam filter, of which 5 were not actually spam. So in other words, 5 were false positives. And there were 2 spam emails that were not caught by the filter that made it to my inbox. So in other words, I had 2 false negatives. So I have 2 questions. One is that assuming that an email is spam, what is the likelihood of being trapped by the filter? And the second question is that assuming that it's trapped by the filter, what is the likelihood of it being spam? And here is where you can start to see the relationship between the 2x2 contingency tables and information retrieval. For example, sensitivity being equal to recall and precision being equal to positive predictive value. The reason why I included this example specifically is because we have incomplete information. We don't have enough information to fill out the entire 2x2 table. But what I want to demonstrate is that you don't always need all the information. And in fact, they might try to throw you off on the exam by giving you just enough information to answer the question without filling out the 2x2 table. So going back to our initial definitions, if an email is spam, the likelihood of it being trapped is equal to is basically the recall. It's the probability of a positive test given the presence of disease, which is also the sensitivity. And if it was trapped by the spam filter, the likelihood of being spam is the probability of disease given a positive test, or the precision or the positive predictive value. So again, I'm drawing the analogy between spam and a disease state, but I think the biostatistical principles are still relevant. Recall, precision, sensitivity, positive predictive value, so on and so forth. Here's our 2x2 table. I don't know the number of emails that were not trapped and not spam, and I actually don't need it to answer this question. I put the gold standard at the top. Again, that's the disease state where you have spam and not spam. And then I have the search strategy or the spam filter on the left where I've got what's it trapped or not. What I know is that there were 34 emails that were trapped by the spam filter, of which 5 were not spam. And that means that there were 29 emails that were trapped correctly because they were identified as spam. I also, from the problem, know that 2 emails made their way into my inbox that were spam but that were not identified by the filter, which means that there's a total of 31 emails that were spam in the one day that the system ran. And what you should be able to tell is that this is enough information to calculate the sensitivity, because that's the first column, and the positive predictive value, because that's the first row. So the first question, if it's spam, what's the likelihood of being trapped? Again, we said that that's the recall of this spam filter, and that's 29 divided by 31, which is my true positive rate, or 94%. And conversely, 1 minus that, or 6%, is my false negative rate. So there's a 94% chance that if an email is spam, it'll be detected, which means there's a 6% chance that if an email is spam, it will not be detected. It will be missed by the spam filter. Next, if it's trapped, what's the likelihood of being spam? That's the precision. Precision is 29 divided by 34 in this example. The 29 true positives divided by 34 that were trapped total, which gives me 85%. And that means that I had 15 out of every 100 trapped emails are not spam. For me personally, that was an unacceptably high false positive rate. I had to keep going to my spam filter to see if any of my expected emails were trapped incorrectly. And it led me to go back and refine that spam filter numerous times to get to where I accepted the performance. But this is an example of how you might apply these 2x2 tables to something like a search strategy. You can also use these to characterize the utility of decision support rules. If you think of the trigger to fire a decision support rule as being equivalent to a diagnostic test. So a number of slides ago, we talked about the trade-off between sensitivity and specificity, and I wanted to explore that in a little bit more detail. Consider a lab test that's conducted in a population where we know there's people who don't have the disease and people that have the disease. And we're trying to say, what is the ideal criterion? What is the point above which we should say the test result is abnormal and below which we should say the test result is normal? Well, I can represent that using this plot here, and let's assume that your normal population has a distribution represented by the blue curve, and the disease population has a distribution that's much wider that's represented by the red curve. And the y-axis here shows the number of patients at any given point in that distribution. And, so normal patients have a mean with a standard deviation about which they vary. Their test results tend to be lower than the disease population, who have a mean and a higher standard deviation, whose test results happen to be higher. But the way I've drawn these graphs, and this is true for a lot of biologic things, those two curves overlap. There's a point at which the line between normal and disease actually blurs. And so the challenge becomes, where do I pin my criterion? Where do I say that this test is normal or abnormal? And what you should be able to tell is where that orange line is actually determines how many false positives and false negatives I have. So if I move that orange line, my test threshold or criterion, to the left, I can reduce my false negatives, but I will necessarily increase my false positives. And in this example, moving the test criterion to the left is the equivalent of making my test more sensitive, right? I'm saying that I'm lowering the threshold to say that a patient has disease, such that I can try to reduce my false negatives. Conversely, if I move my test criterion to the right, I can make it more rigorous and I can try to eliminate my false positives, but I'll do so by increasing my false negatives. I'll reduce my sensitivity by trying to optimize my specificity. And that's why there's this trade-off that because for many things like lab tests, there's not a clear demarcation between normal and abnormal. There's often a gray zone. There is this direct trade-off between the two. If I wanted to understand in more detail that trade-off, I have to rely on a technique called the receiver operating characteristic curve. It's often abbreviated as the ROC curve, and we'll refer to it as the ROC curve. But it's a visual representation of the trade-off between sensitivity and specificity, and the goal of this is to assist you in detecting signal from noise. Basically, what you're graphing is on the y-axis, you're graphing your sensitivity or your true positive rate. And on the x-axis, you're graphing your false positive rate, 1 minus specificity. And each point on the graph represents the performance of that test as I change the test threshold or the test criterion. In other words, what I'm trying to model is, if I move the criterion way to the left, what does that do to sensitivity and 1 minus specificity? Versus if I move it way to the right, what does that do to my sensitivity and 1 minus specificity? There's an interesting thing that happens here, which is that the better the test is at discriminating between true positives and false positives, the larger the area under the curve. So this is an example of an ROC curve. And notice that on the y-axis, I've got my true positive rate, and on my x-axis, I've got my false positive rate. And if I pick a point like that red square, what I'm saying is that if I tune my test criterion such that I can achieve a sensitivity of 90%, I will unfortunately have a specificity of about, a false positive rate of about 25%. I could make my test more sensitive, but then I'm running into sort of only marginal gains, where now my false positive rate is much higher. Conversely, if I change the criterion to something else to try to minimize my false positive rate, I would do so at the expense of my sensitivity. My sensitivity would go down to 40% if I got to a false positive rate of about 5%. So these 3 points that I've described here, the green triangle, the red square, and the orange circle, unfortunately, in the scenario where you have the green triangle, you have a low true positive rate and a low false positive rate. So that's not very helpful for us. If I have if I go all the way up to the other extreme, which is the orange circle, I have a slightly better true positive rate than I do with the red square, but at the expense of a very high false positive rate. So that's not good for us. I'm not willing to optimize sensitivity at the expense of a very high false positive rate, because then I'll just be evaluating every patient for the disease unnecessarily. And so what you find is that that inflection point in the graph, the sort of shoulder of the ROC curve, where the red square is actually the best trade-off. It's the one that gives me the best true positive rate for the lowest false positive rate. So if you're shown a graph like this with 3 discrete points and they say which of these 3 test criterion is optimal for discriminating disease from wellness, you would choose the one that's right at the inflection point, or in this example, the red square. Another way that you can use ROC curves is not just to look at test criterion for a single test where you're varying the threshold, but comparing the performance of different tests. You're trying to see which test is better at actually discriminating from disease. And this is where you have to look at the area under the curve. Now, remember I said that the tests that are better at discriminating disease state from wellness are the ones that have a higher area under the curve. So in this example, if they said, here's 3 tests, one represented by the green, one represented by the orange, one represented by the red, which test is the best test at discriminating disease and wellness? You would say it's the green one because it's the one that has the highest area under the curve. And one way to sort of conceptualize that is take a look at that red line. If that test has a direct trade-off that every gain in sensitivity of true positive rate is reflected as an unfortunate increase in false positive rate also. So I cannot achieve a high sensitivity without shooting my false positive rate through the roof. Meanwhile, the green curve has a steep slope in the initial spot there, such that I can get to pretty decent true positive rate and not have a horrible false positive rate. Okay, now we're done talking about ROC curves. Let's move on to another topic. Let's look at relative risk. This is completely different. It has nothing to do with 2x2 contingency tables. Relative risk is an interesting concept. It's basically the ratio of the probability of an event in an exposed group to the probability of an event in an unexposed group. And so it's the ratio of 2 different conditional probabilities indicated by this equation here, that the relative risk is equal to probability of disease given exposure divided by the probability of disease given no exposure. By definition, the relative risk must be positive. If the relative risk equals 1, that means there's no association between the exposure and the outcome. If the relative risk is less than 1, it means that there's a decreased risk. So in other words, with the exposure group, you see a lower probability of disease. It should follow that if your relative risk is greater than 1, that means that there is increased risk. So here's a couple of real examples. The relative risk of lung cancer if you are a current smoker, as defined by greater than 25 cigarettes per day, is equal to 10. That means the probability of disease, probability of lung cancer given that you're a current smoker, is 10 times higher than the probability of lung cancer if you're not a smoker. Another example, this is one where there's a decreased risk or a protective effect, that the relative risk of prostate cancer if you are Asian is 0.4, that's less than 1. And you can see that there are these sort of defined zones to define the strength as either weak, moderate, strong, or very strong. So on the decreased risk side, if the relative risk is between 0.7 and 0.9, that means that there's a very weak relationship, but slightly decreased risk. Moderate is 0.4 to 0.7. Strong is 0.2 to 0.4. And very strong is 0.2, less than 0.2. So in other words, if your relative risk is less than 0.2, that means that there's a very strong decrease in risk in patients with the exposure. On the opposite side, on the increased risk side, you can see that there's a similar set of statistics. And basically, if your relative risk is 7 or higher, that means there's a very strong increase in risk in the exposed group. So let's look at surveillance culture. Let's look to a specific example. We're looking at surveillance cultures in an ICU used to identify patients with MRSA or methicillin-resistant Staph aureus colonization. And I want to know, what's the relative risk of skin and soft tissue infections, or SSTIs, among patients with MRSA compared to those who do not have MRSA? So in this example, MRSA is the exposure, and the SSTI is the disease state. Okay? So all we have to do is find out the probability of SSTI among patients who have been exposed to MRSA divided by the probability of SSTI among patients who do not have MRSA exposure, and that'll give us our relative risk. And here's how you would do that: that the relative risk in the risk in the exposed group is 12 out of 89, and the risk in the unexposed group is 4 out of 283, which gives me a relative risk of 9.6. And I know from that previous table that because that relative risk is greater than 7, that means there's a very strong increase in risk of skin and soft tissue infections among patients who are exposed to MRSA. Colonized with MRSA. So, let's talk about Bayes' theorem, and this is covered elsewhere in the curriculum as well. But Bayes' theorem is basically the notion that you can calculate the posterior probability of disease if you know a few other things. So in this example, let's say A is the probability of disease and B is the positive test. So what Bayes' theorem would say is the probability of A given B is equal to the probability of B given A times the probability of A, and all that divided by the probability of B. Now, we know what all of these subterms are, actually. So the probability of A given B, so the probability of a disease given a positive test, is the posterior probability, post-test probability. We know that the probability of a positive test given disease, which is that second term, the PB vertical pipe A, is the sensitivity. We're saying that that's going to be multiplied by the probability of A, where A is just the probability of disease itself, or the prior probability, or the prevalence. And then all that gets divided by the probability of a positive test, which is the sum of your true positives and your false positives. So here's the thing. You don't have to memorize Bayes' theorem. All of the time, every one of these calculations where we've calculated the posterior probability using the positive predictive value is basically you're replicating the math of Bayes' theorem without using Bayes' theorem, and you'll end up getting the exact same answer. We're going to define another term, and I'll pull this all together at the end, called the likelihood ratio. To understand likelihood ratios, we need to understand the difference between odds and probability. Most of us probably use these terms interchangeably. They mean very different things. If you do any parimutuel horse betting and things like that, you probably are actually more familiar with dealing with odds than you are with probability. But most of us, when we say the word odds, we actually are referring to probability. The difference is that the odds of something are equal to the probability of that thing happening divided by the probability of that thing not happening. So, in other words, if I flip a coin, the odds of me getting heads are 1 to 1. But that means that the probability is 1 in 2. There's a 50% chance of getting heads, and I'm equally likely to get heads as I am to get tails. Now let that sink in a little bit, that the odds of something happening are equal to the probability of that thing happening divided by the probability of that thing not happening. And that means that, for example, if I say that an event has 1 to 3 odds, what I'm really saying is that for every 4 times it happens, it will happen once and it won't happen 3 times, or that there's a probability of 1 in 4, or 25%. The reason why we care about odds is because we have to use odds when we talk about something called the likelihood ratio. And the likelihood ratio is derived from sensitivity and specificity. It's a number that has this unique property that this one number reflects both the sensitivity and specificity of the test. So if you can imagine having one portable number to remember about a test, the likelihood ratio is the one you want. There's two flavors of it. There's the positive likelihood ratio and the negative likelihood ratio. The positive likelihood ratio is equal to the sensitivity divided by 1 minus specificity, or the true positive rate divided by the false positive rate. The negative likelihood ratio is 1 minus sensitivity divided by specificity, or your false negative rate divided by your true negative rate. And the post-test odds is equal to your pre-test odds times your likelihood ratio. So this gives us a little bit of a roundabout way of figuring out post-test probability. And it goes something like this. If I know the pre-test probability of an event, and if I convert it to odds, multiply it by the likelihood ratio, then I'll get the post-test odds, which then I can convert back to probabilities to get the post-test probability. So a lot of steps. You end up getting the same answer as if you did it with the 2x2 table, but in some cases and in some questions on the exam, this may be an easier approach if they give you this information. Let's say they give you the likelihood ratio, but they don't give you the sensitivity and the specificity. So let's do an example. In this example, I, as a Star Wars fan, am looking at how to predict whether somebody is going to be a Jedi or not. And I'm going to do that based on something called the midichlorian count, which if you're a Star Wars fan, you'll recall that at some point George Lucas introduced into the Star Wars canon this idea that being a Jedi is actually an infectious disease, and that the more midichlorians you're colonized with in your bloodstream or in your body or wherever they are, the more likely you are to have a Jedi. And Anakin Skywalker had an amazingly high midichlorian count. So here's the 2x2 table that we have that Jedis who test positive for midichlorians, there's 19 of them, but there's also 7 people who are not Jedis who have midichlorians floating around. And the other numbers are there as well, that there's only 2 Jedis who don't have a high midichlorian count, and 439 patients or people who are not Jedis and have a low midichlorian count. So it's a convoluted example, but I can calculate the sensitivity and specificity from this. The sensitivity is 19 over 19 plus 2, or about 90%. The specificity is 439 divided by 7 plus 439, or about 98%. And because I know that the LR positive is sensitivity divided by 1 minus specificity, I can figure out that the LR positive of this is the positive likelihood ratio of the midichlorian test is about 58. Okay? What that means is that if I know my pre-test odds of being a Jedi and I multiply it by 58, I'll get the post-test odds of being a Jedi. The pre-test odds of being a Jedi in this example are 21 out of 446, and that's basically the ratio of the left column and the right column. Okay? And you can simplify that if you want to. It's about 0.047 to 1. But there are some situations where the math is actually easier if you just keep it as 21 over 446, or 21 to 446. So what I'm saying is that if the test is positive, I would take that 21 to 446, or the 0.047 to 1, multiply it by my known positive likelihood ratio of 58. And now I get that the post-test odds are 1218 to 446, which reduces down to 2.7 to 1. Okay? So previously, there's a 0.047 to 1 odds of being a Jedi. And after I do the test, when it's positive, there's a 2.7 to 1 chance odds of being a Jedi. And you're saying, okay, well, how helpful is that? It's only helpful because I can convert 2.7 to 1 odds back to probability and determine that that's a 73% chance of being a Jedi. So in other words, if you were to do this test and in this population and you tested positive for midichlorians, there's a 73% chance that you're a Jedi. Okay? Now, that was a very roundabout way of doing something that we already knew how to do, which was calculating the positive predictive value, which in this example is 19 divided by 19 plus 7, right? I'm looking at the first row, and I can find out directly that the positive predictive value is 73%. But doing it through odds and LR might be the only way on the test to do it if they didn't give you the sensitivity and the specificity separately. Okay. So let's think of a different variant on this example. Again, the previous example was a little bit forced because we had to calculate the prior odds and the LR positive, and there's really no good reason to have done that. We probably would have just done it directly by measuring the positive predictive value or calculating the positive predictive value. But now that we know the LR positive is 58, it actually does become a little bit easier. If we know the prior probability of being a Jedi is 12%, then we can actually simplify the math of calculating the posterior probability. So prior probability of 12% means there's a prior odds of 12 to 88. The posterior odds is that 12 to 88 odds multiplied by 58, or my likelihood ratio, positive likelihood ratio, which gives me a posterior odds of basically 7.9 to 1 if you follow the math there, and then how I divided the top part by 88. And 7.9 to 1 odds is the equivalent of a probability of 89% if I convert back to probability. So if your prior probability is 12% and you do the test and you're positive for midichlorians, now there's an 89% certainty that you have the disease. So notice the shorthand I've done here, which is that to keep the math easier, you can keep the odds in their original notation. You don't have to reduce it. In other words, I could have kept it as 696 over 88, 696 to 88, rather than reducing it down to 7.9 to 1. Personally, this is still too much math to have to do to calculate this thing, and a doctor named Fagan actually agrees. And he came up with this thing called the Fagan nomogram, which is was intended to be sort of a pocket reference to allow you to quickly calculate posterior probabilities based on likelihood ratios and pretest probabilities. I think it's a useful exercise. I've listed to a diagnostic test calculator here by Alan Schwartz, which is listed at the website below. And basically, it allows you to plug in the LR positive and negative and the pretest probability, and it will give you the posterior probability in the situation where the test is positive or in the situation where the test is negative. So if we plug in the exact same information from our previous Jedi example, where a prevalence was 21 out of 467, which gives us a prevalence of 4.5%, we can see that the when the test is positive, the probability of being a Jedi exceeds 70%. And conversely, if the test is negative, the probability of being a Jedi is only 0.5%. Now, this is an interesting phenomenon where there's a lot of tests that are like this, where the negative test is more helpful. In other words, it does a better job of ruling out the disease than the positive test does of ruling in the disease. And all of these Jedi examples aside, there are some applications in actual clinical practice, and specifically because a lot of these LR likelihood ratios, positive and negative, are just published, and they're easy to find. So, for example, we know that the rapid strep test has a positive likelihood ratio of 15.2, which means that if it's positive, the likelihood ratio is 15.2. We also know that any ST segment elevation on an EKG has the positive likelihood ratio of 11.2 for diagnosing myocardial infarction. which is better than the likelihood ratio for MI if the patient presents with pain radiating to both arms. In that case, the positive likelihood ratio is only 7.1. Similar to, but not exactly like relative risk, likelihood ratio also has a range of values. The likelihood ratio varies between 0 and 1, and any value, likelihood ratios range much more widely than 0 to 1, but values between 0 and 1 mean that you have a decreased probability of having the disease if the test result is positive. And values between 1 and infinity increase the probability of disease. And you can actually put some estimates around this, that if your likelihood ratio is positive 10, that roughly increases your posterior probability by about 45%. If your likelihood ratio is 0.1, that decreases your probability posteriorly by about 45%. Okay, so let's put this all together and do an example. A 16-month-old female comes to your emergency department with a high fever without an obvious source. You intend to order a urinalysis, and you want to determine if the patient has a urinary tract infection. How would a positive test influence your decision? How would a negative test influence your decision? Those are the two questions at hand. Let's say that in the vignette they give us the likelihood ratios. The published positive likelihood ratio is 5.6. The published negative likelihood ratio is 0.03. Let's say that the question also gives us the prevalence, the pre-test probability of 3.3%. So if you're a febrile female from 2 months to 2 years of age and you present to an emergency department, the likelihood that you have a urinary tract infection is 3.3%. So the question is, can we use that Fagan nomogram to help us determine the probability? And you can also, again, do this math. You can do this by hand, since we know the prevalence and we know the LRs. But let's do this with the Fagan example. So I urge you at some point to pull up this website, plug in those numbers. And this is what you should get. That when you pin your pretest probability at 3.3% and you enter the LR positive of 0.56, your posterior probability is now 16% roughly. And so that means that I was only 3.3% certain that the patient had the disease before the test, and now the positive test makes me 16% certain, which is not fantastic. But look at the negative result, that in the situation where the patient tested negative, I went from about 3.3% down to 0.1%. So in this example, a negative test effectively rules out the disease. And that's a great example of a good screening test. That screening tests have this principle that they help you rule out disease. Okay. This is also an example of where you can use these kinds of biostatistical principles to help you create clinical pathways. So, for example, you might say that this test is so good at ruling out a urinary tract infection that if the patient screens negative, you can stop all additional testing. You don't have to do a urine culture or anything like that. So again, using the biostats to your advantage, you can actually come up with better clinical practice guidelines. You can come up with better clinical decision support rules and so on. So thanks for bearing with me. That was a very long lecture, and I hope you enjoyed it. Again, this is a very high yield set of topics. I would encourage you all to review the 2x2 tables and all the math that was reviewed in this lecture. A lot of suggested additional reading here. Some of these are textbooks. Some of these are useful references for things like the Markov models and Bayes' theorem. And then the good thing about biostats is that there's no shortage of courses online. These are a bunch of freely available resources on the internet that I would encourage you to check out. Specifically, some of these online statistics lectures, if you really want to delve into some of these things like the trade-off between sensitivity and specificity, the predictive values, screening tests, receiver operating characteristic curves, and so on.